We built what became first PC, if you will. We had an 86 chip we got from Intel. We built the board, we built the memory cards, we built the disk controllers, we built our own computer. Microsoft was a $10 to $20 million company. Today it's worth $3 trillion. It's also considered the worst deal of all time if you take the perspective of Tim and myself. We didn't realize that they were selling this to IBM. If we had known that, we probably would have done something different.
You said the real shift isn't AI, it's autonomy. What do you mean by that?
AI's been around for a long time. Since the 1950s. Neural networks, those ideas go way back when, even when it was just in hardware. I was involved in AI in the early days, in the 1990s. At the end of the day, that's a very powerful calculator, a generating calculator, generating content, generating code.
Generating even movies now.
Generative aspects of AI right now is unbelievably incredible, right? But really, what is happening underneath all this is this urge to move toward autonomy. That experience of just hearing the frogs croaking, very impressionable upon me. And then a mile from there, we're building DOS. One's digital, the other one is analog.
Jim, what separates people who survive inflection points from those who miss them?
Well, probably bringing something unique to the table. What you see in technology is a lot of people racing after some invention that's already been made. And so people just jump for it. So you see, like in large language models and agents and so forth, you see a lot of venture capital running after that. And there'll be hundreds, if not thousands of companies that just come and go. And the reason is that they didn't actually offer anything different. So what happens is as these large hyperscalers scale, they end up enveloping everything that these small startups have built. And it's just part of what they do, or they require these companies. So you really have to come up with something unique that's differentiating, that truly adds value to the market.
I think one particular book that I always refer to on this show, and even in my conversations with founders, is the book about, so it's a book by the ex-CEO of Intel, Only the Paranoid Survive, which centers a lot around inflection points and what they actually mean. For the purpose of the audience, what does an inflection point from a perspective of a company mean to you?
It means that we've been doing the same thing for quite some time, and now everything changed. And did you follow that line? Were you there? Were you ahead of it? Were you with it? That's an inflection point. Mm-hmm. Like, I think you're referring to Andy Grove's book.
Mm-hmm. That's right.
Right. And, Andy Grove oversaw the development of CPUs, right? It was mostly microprocessors way back in the day. And the CPUs went from the 4004 to the 8008, the 8080, 8086, and so forth. He was the one that was out in front. Of course, Motorola was out there too, but he was out there with probably the greatest vision of where everything was going. Of course, they invented the term, Moore's Law. Gordon Moore was there. And so that company, if any company, would have seen where things are going. Unfortunately, they sort of missed the inflection point that came later. Right, in 1999, little NVIDIA at the time, created their GPU. Mm-hmm. And we were just using it for graphics, and that was just sort of a side hobby in the overall market of technology. But now look where it is now. Mm-hmm. And they sort of missed a couple of inflection points. One was the AI, and the other was the phone. So even though they are the authors of this inflection point, they also sort of didn't see the other inflection points that came.
As far as separating the companies that see that inflection point and the ones that don't, when we look at that particular scenario, being the author of the book, having seen that inflection point earlier on in the 80s and during their cycle of growth, as you said, they missed a few, especially with the most recent one with AI. What separates the two? And by the way, the reason I'm asking this question, Jim, is because I'd like to double down on your background a lot with this particular topic, from how you went about seeing different shifts and different cycles in tech, having sold one of your first companies to Amazon. But just going back, what are the key indicators that tells you this company is perhaps missing an inflection point? Is it the people? Do they lose tenacity? Do they lose the hunger, the drive? Do they have some sort of market insight that allows them to see around the corners? What separates the two?
Well, you either have an innate drive or you don't. I don't think that's something you learn. I think you're born with it. Mm-hmm. And then you have to match that with guts. You got to take some risk, right? So, and I've been around these risk takers. I'm a risk taker myself. We're all risk takers out here, but it's so this guts and innateness that you have to do to really take advantage of something. And sometimes it's ruthless. We can talk about, some of my origin story and some of the ruthlessness that went out with some innate insight, guts, and so forth to get to a point.
Let's go back to the beginning and your story. One of your first startups that you sold to Amazon. I think that's a very interesting one that I feel will tap into a lot of these areas around inflection points, around missing or seeing the opportunity. You've been part of some very historical moments in the PC and the technology era. For the purpose of the audience, the people that don't know you, I'd love to get a bit of background on yourself, Jim, and where it all started for you.
Yeah, so I grew up in the Seattle area, a little town called Tukwila. And Tukwila wasn't known for anything until this large shopping center went out in 1968 called South Center. And then all of a sudden things changed. People came to the city to shop. But what South Center did is to me, it was kind of a sad moment, because as a kid, there's a gigantic pond that was down there, about a 150-acre pond. And I would go down there, collect frogs, and look for fish and all kinds of things. That was my life. I just loved going down there as a child and traipsing through the reeds and looking for frogs and so forth. And in this little area, not too many years later, growing up, Seattle Computer Products started up in Tukwila. And Seattle Computer Products was this small company that had an idea that they wanted to beat the mainframe with a 16-bit chip. Now, I had been at the University of Washington, and there's an interesting history there that the first 16-bit computer operating system, called CP/M, was written by a PhD guy named Gary Kildall in the 70s, early 70s. And that he sold tens of thousands of these things to hobbyists running this operating system. And I'd been there. I took a class from a guy, Professor Ed Lazowska. He was like 26 at the time. He later became the chairman of the computer science department. And I was really enthralled with computing and so forth. So I bought my own Apple II computer, and I had it in my dorm. And we were doing all this programming in Pascal, either on VAX machines, which are mini computers, or mainframes. I was a research assistant as well out there working on the mainframes, controlled data computers. But I wanted to have control myself. I want to be able to do my own stuff, do all my assignments, even do my tests. And so I walked out of the final exam with Professor Lasowski. He said, "You're going to fail." I said, "No. Do you have office hours?" So I showed up a couple hours later and I brought my Apple II computer from my dorm. I set up the computer and the disks and the monitor. He said, "What's that?" I said, "It's a personal computer." Like, "Well, what can you do with it?" "Well, I'm going to do my final exam that you said I was going to fail." So I did that in front of him, about a 20-minute exercise. And he said, "Wow, that's pretty amazing." Well, what was interesting was Apple II had this Apple-DOS operating system, and it wasn't much to brag about. But Microsoft, back in the early days, they had created this thing called the soft card, and it was running CP/M on a Z80 chip that you'd plug into the Apple II, which had a 6502 processor. My whole world was there. I could do Pascal on CP/M. I was loving it. And it turned out that the person who designed that card was a guy named Tim Patterson at a company named Seattle Computer Products in Tukwila, where I grew up. And Tim had recruited me because I had been using CP/M, and he needed to create an operating system because he couldn't get a 16-bit version of CP/M. It was only on for 8-bit computers. So I went down there to Tukwila, my old stomping ground, and I showed up, and he said, "Hey, let's come join the team here." It wasn't much of a team, a very small company. And we built what became the first PC, if you will. We had an 86 chip, we got from Intel. We built the board, we built the memory cards, we built the disk controllers, we built our own computer. And it was pretty amazing at the time because I had just come from working on mainframes and minis, and now I'm working on this, at the time, super fast mainframe of my own that had a 86 chip on it with 29,000 transistors. Today we have 10 to 20 billion transistors on the chips in our phones, right? This is early days, but it was quite significant.
What was that like, being part of that? I'd say part of history when it comes to technology and the journey that, what happened after with the industry and how things changed. What was it like for you when you look back, especially now in hindsight?
Well, in hindsight, there's some interesting insights, right? You refer to the inflection points. Okay, there's a major inflection point going on. So in the 1960s and 70s, we'd gone from tens to hundreds to thousands of computers that were out in the market. But these weren't household, these weren't personal computers. These were hobbyists and universities, doing research, government, banks. These computers just weren't prolific. People weren't using them. So to the idea of a personal computer or a business computer or a computer on your desktop where you could kind of control your destiny, in your office, that was an inflection point. Now, we were more interested in just beating the mainframe with something fast. Like 16 bits was just unbelievable back then. So let's go do it. But the inflection point was that something had to happen where we'd go from thousands to millions. And there were a couple things that did that. Well, one was someone kind of had to take the plunge. Now, we were a small company. There was no venture back in those days, really. Microsoft was probably worth $10 to $20 million at the time. They had received some venture capital, but it wasn't a big deal. No one really knew about it. We didn't talk about that. And the inflection point was, what if a major computer company got into the space of personal computing? So what had happened is IBM had known about this soft card, this thing I had on my Apple II, and they had a secret project where they were going to come out with a personal computer, the IBM PC. And they needed an operating system. So when they went to Microsoft was trying to sell them languages. They said, no, we don't want languages. Because Microsoft didn't have an operating system. People don't remember that. They just had languages and games and things, right? And they said, no, we want an operating system because that CPM thing that's on your soft card that's on the Apple II, why can't we just license that? Well, they said, that's not ours. So Bill Gates called Gary Kildall and said, hey, look, we got to do a deal. He didn't work one out. He said, these guys are going to come talk to you. So IBM went to talk to Gary. They didn't work out a deal either. So Paul Allen and Steve Ballmer, so Paul and Bill Gates had formed Microsoft prior. Steve Ballmer was a little later addition, kind of the sales guy. And Paul knew about the soft card because Tim designed it originally. Tim Patterson at Seattle Computer Products designed the soft card, but they used a different manufacturer than Tim. So Paul and Steve came down to see what we had here. They're going to do a deal. And so what we demonstrated to them was QDOS. And the reason we did QDOS is because Gary Kildall wouldn't give us a 16-bit version of the operating system. He only had an 8-bit. Later, he came out with one, but the horses had left the barn. It was long gone. And so what we showed them was, I actually have the original card. We built our own card. So this is a Seattle Computer Products 8086 CPU card.
This is the first one.
Now, this is the first one. You can see the wire wrap back. When you build your cards and you put everything together, it all works great until.
So just for the purpose of the listeners who aren't watching the episode online and probably listening to this on Apple Podcast or Spotify, just explain what is it that you're showing us there?
Well, so Tim had designed what was called an S100 card. S100 was the bus that you plug your cards into your computer, and S100 was sort of the standard in the day. PCI later with IBM and so forth, but S100 was a standard. So these parts at the bottom here is what plug into a computer. So we bought a standard S100 bus chassis, and then we said, well, we need to run it with a CPU. So we went to Intel and got an 86 chip right here, and then we've got a bunch of memory chips, and we built memory cards as well. And we bought disk controller cards, bought disk controllers. There were these large disks. Back in the day, we had these like 8-inch disks. Like this is DOS 1.25 or something like that. I still have it. So we would buy all this stuff and then we'd build it. Mm-hmm. And Tim was an electrical engineer. And there was another guy, Pat Opalka, who they built all this hardware. And so Tim needed to do something if Gary Kildall wasn't going to give us a 16-bit version. And we didn't know what the licensing would cost and so forth. So Tim just said, I'm going to go build this thing. So he built QDOS. Well, what had happened then was this inflection point was coming. This is where we're going to go from the thousands to millions. It's a triple order magnitude inflection point. Those are the good ones. When you go from triple order magnitude, 1,000 times what was before. And so IBM needed this thing. They came down to us. We demonstrated it on that card, and they worked out a deal. It wasn't a good deal. In fact, on the one side, it was considered by many the greatest business deal of all time because, Microsoft was a $10 to $20 million company. Today it's worth $3 trillion. It's also considered the worst deal of all time if you take the perspective of Tim and myself, Rod Brock, the CEO, Pat Opelka, and others. We looked at that, and for us, it was a deal that could get us to buy some more hardware to keep up building computers, but we didn't realize that they were selling this to IBM. If we had known that, we probably would have done something different. So, inflection point is happening. Microsoft is doing the deal with IBM. Microsoft's doing the deal with us. Mm-hmm. And then this amazing moment happens in history where I believe it was August of 81 in Byte magazine, they had the advertisement for the IBM PC. People saw that, they started ordering it. But the problem was at the time is, what are you going to use this for? The only thing we really had were languages like Pascal and Fortran and C and BASIC. And that was really how Microsoft got started with these languages. But then the next multiplicative factor to the inflection point was a couple years later, 1983, Lotus 1-2-3 came out. And it was a spreadsheet that had graphics on it that ran super fast on the IBM. And that caused people to plunk down $5,000 for a computer by buying a $495 spreadsheet package, right? So they wanted the spreadsheet and the computer was $5,000. Sure, I'll buy that because I have all this productivity. And then also what was happening was the internet came out in 1983. A lot of people think it came out in the 90s. That's the web, HTTP, but this is TCP/IP came out. So now we could send email anywhere around the world if you had that protocol on your computer. And so that was where we went into from thousands to millions in the mid 80s. People were doing email, not everybody, but it was happening and we're productive now with the computer.
Just so we understand this, from the perspective of market shifts, the internet was the amplifier. Without the internet, we wouldn't have seen the growth that came from that particular moment in time. Is that fair to say?
Yes and no. So January 1st, 1983. January 1st, 1983 was when TCP/IP kind of came together. We said, hey, we've ratified this. This is the internet now. We were gone from the ARPANET to the internet. But also in January 1983, Lotus 1-2-3, Mitch Kapoor came out with this 1-2-3 spreadsheet. Same month. But no one was really, internet didn't take off, right? People didn't really know what it was. Lotus 1-2-3 took off. And so then you had Compaq and you had Dell and you have all kinds of computer manufacturers that came out that then eventually beat IBM at their own game by masterfully figuring out how to manufacture these things inexpensively and create market demand. Then Microsoft was on top of that because they're selling these licenses. And then they came out with things like Office and so forth on top of that. So Microsoft had a bit of a monopoly on the PC game. Now, Apple was out there with their stuff too, competing. And we know the story on all those infamous meetings between Jobs and Gates. But that was the dynamic tension that was going on there, causing this incredible explosion in PCs. The internet really didn't have a huge effect until the 90s.
Yep.
With the web.
Another area that I'd like to kind of tap into is this idea of AI versus autonomy. And from conversations you and I have had prior to this recording today, you said the real shift isn't AI, it's autonomy. What do you mean by that?
AI's been around for a long time. I mean, since the 1950s. Neural networks, those ideas go way back when, even when it was just in hardware. I was involved in AI in the early days, in the 1990s. So I think around the early 90s was the second AI winter had gone through, where there's all this hype about AI and it didn't deliver, and the market's saying, we don't want to buy AI, it's not working. And in the mid 90s, I had a company called Cartia, which was a tech transfer out of Battelle Labs in Richland, Washington, the home of the Manhattan Project. A lot of PhDs there. And they were doing some AI, so I went there, joined them, and did a tech transfer. And what had happened back in the 90s was this idea of support vector machines from the 60s, a really old AI concept in statistics. A paper came out, much like the Transformer paper in 2015, which lit the fire to the large language models. The support vector networks came out, and we built a really interesting AI application for querying the internet. And we ended up, taking that as far as we could, and then Amazon bought the company. And so that was some of the early sort of scaled out AI we're the recommendation engine at Amazon, trying to show the world how AI could be used. But this is like very minuscule application of AI. Today, what's happened is we've gone at scale. And so the large language models of Gemini and OpenAI, Anthropic, etc., they did what I was trying to do way back in the day. I was trying to go grab, in fact, I went to go see Lycos, which was one of the early, there's Inktomi and Alta Vista and Yahoo, pre-Google. Yep. There's all these web crawlers. And I wanted to use AI on the web so you could do natural language. And so you just type natural language and your queries would come back, right? But at the time, it was so expensive to get even 10 terabytes of data collected that they weren't willing to go build these models that I wanted to do with CARTIA to go put AI on the web. So many years later, in fact, 2 decades later, the large language model came out and the transformer algorithm. And now those guys had the money to go and grab all the web information and all information you can get digitally and run this transformer over it. And now it's amazing. You can find out anything you want instantaneously. And so when you look at what AI is doing, it's absolutely amazing. Back in the 70s, we had calculators for the first time with CPUs in them that allowed us to not have to do long math, or use slide rules. Today, we have all the information in the world, like a calculator, instantly available to us with this tokenization of information. But at the end of the day, that's just a calculator again, a very powerful calculator, a generating calculator, generating content, generating code, doing all the things that we do digitally, much faster.
Generating even movies now. I don't know if you've seen recently.
Generating movies, the generative aspects of AI right now is unbelievably incredible, right? Mm-hmm. But really, what is happening underneath all this is this urge to move toward autonomy. Mm-hmm. Now, when we went from the 70s to the 80s, where we now had personal computers, we could be sort of autonomous doing work on computers. Yep. And then networks came out and we connected them together. And then the internet came out, we connected everything together. We have all this distributed information. What we don't have is distributed intelligence.
Right. So when you say autonomy in this context, what are we talking about exactly?
We're talking about the inflection point where we go from people using computers to agents using computers, agents talking to agents, agents talking to robots, people talking to robots, people talking to agents, robots talking to devices, devices talking to applications, applications talking to humans, humans talking to agents, all that. So what's happening is we're moving away from sort of this client-server world where you have a client, you got a server, you interact with it, that's the web, to this diffusion of everything. And intelligence moves to where it needs to be, and then it has discovery of what it needs to do. What skills do I need out there to perform these tasks? Who can do this? Who can I delegate this to? Now, if we look at the history of computing, IBM sort of built the first operating system in the 50s for mainframes. And then we had DOS and we had, Mac operating systems and so forth, Linux. But where are we now? We don't really have a distributed operating system, right? We have operating systems and we didn't have distributed information, but we don't have a distributed operating system. So where autonomy is important is allowing everything to be where it needs to be, to move to where it needs to move, and have the intelligence it needs to have, and to interoperate or collaborate with other intelligent entities, if you will. And so the difference between the big push and the breakthrough and inflection point of this AI and large language models and autonomy, these things have to move to some place. Now, all the focus right now is in doing reasoning and automation and generation, content, code. But where things will end up is a network, right? Just like the web solved the wide area network problem that we couldn't solve with LANs. The web solved this distributed information networking thing. The next network, I call it the paranet. We developed this thing called the paranet. Para means alongside, so everything alongside each other, collaborating. The paranet is the next layer above the internet. Right. It's on the internet. There's this 7-layer protocol stack. HTTP with the web is layer 7. Layer 8 is where you abstract all that below and you say, hey, I have a bunch of things we'll call actors. Now, an actor can perform for an agent, for a robot, for a human, for a device, for an application, for an API, etc. You're now on this network. where things can collaborate with each other. And now it's a different kind of network because it's an autonomously oriented network. It says, hi, I'm an actor. Here's my skills. I'll tell the network what I can do. I need these skills. Hey, network, who has these skills? I'll put a skill request out. The network will solve that for me. So where we're going is to this autonomous world of networking on the internet. There's the idea of what's called an overlay, a network overlay. An overlay means you've got this protocol you're running, and it can run on all the existing hardware, but no one else knows about it. That's how the web works. That's how a lot of protocols work. So the ParaNet is this overlay that allows autonomous actors to collaborate with each other.
It's very fascinating. So what you're basically saying is, if you use the example at the start of the show today, we're currently probably sitting in the late 70s to where that inflection point happened for you back then to where AI is today.
Yeah, the way I like to look at that is that 70s to 80s was thousands to millions, triple order magnitude inflection point. So then 80s to 90s to 2000s was millions of people using computers to billions of people using computers, right?
Right.
And what you're saying is the next inflection point, what is it? Well, it's a triple order magnitude step function. That's billions to trillions. Well, we're not going to go billions to trillions with humans.
Yep.
And even though we're generating agents, maybe 1 million agents a day right now, they don't have a place to work. They don't have a trusted, safe, secure way on how they should operate. So we've invented a new kind of security, a way that they can have trust amongst each other. So when they discover each other, they can work, they can be assured they're going to complete things the way they should. And with this actor model, on top of the agentic model, we use deterministic AI. So we actually had to build an AI language. And believe it or not, if you read everything about AI in the last 40, 50 years, no one's come up with an AI language. The last language that was based on AI was Prolog. And it was interesting. But we created a language called Paraflow. And Paraflow says, I have a number of actors. I want to delegate work to them. They need to discover each other through a protocol that says, you have a skill that can match to what I need. Great, go do this. I need to know what you're doing. I need to see what you're doing. I need to create actors who can watch what those other actors are doing. So we created this AI language to be on this network. So the way to think about this is, back in the day in the 90s, I remember when I first saw the web, I was on a Mosaic browser. I was in Paul Allen's office. And these guys came to show it to us. And I said, so Paul and I were asking, so what is this? Well, it's HTTP is this protocol. What's HTTP? Hypertext Transfer Protocol. Okay. And what's this HTML thing? That's a hypertext markup language. So you have language and a protocol, but back then no one knew. It sounded like arcane words, right?
Sure.
For me to then say, okay, how do you go from distributed information to this distributed intelligence? Well, there's a new language called Paraflow, and there's a new protocol called PNCP. It's just as arcane as what Paul and I first heard.
Yeah.
But no one even uses the term. No one ever says HTML or HTTP anymore. You don't hear that. You see it, but you don't hear it because it's just in the water. It's in the billions of connections.
Yeah, of course.
Trillions of connections.
So, Jim, I want to touch on one last topic. I could sit with you for long. We could talk about all this amazing things that have happened in history that you've seen, all these different inflection points. But I want to touch on this last topic as we wrap up this episode today. You are running a cutting-edge tech company, but you're running it from a ranch surrounded by animals. And it's a conversation you and I have had a couple of times. We wanted to do this in person, in fact, at some point. But what does nature understand about autonomy that Silicon Valley doesn't?
Yeah, Silicon Valley has sort of been swept up in a transistor moment, right? The transistor was probably the greatest invention of the 20th century, and it allowed us to create all the stuff we're doing right now. It's allowed us to create all this market capitalization of these huge companies. It allows us to do this podcast right now. But it's not real. Like, even though you and I are looking at each other, if you turn the screens around, there's nothing there, right? So what's real is an analog signal right now coming from my lyrics into your eardrums back and forth, right?
Yep.
That's reality.
Mm-hmm.
And so what we want to do is when we're building stuff, we want to, reflect nature as much as we can. And I've always had that principle, like South Center at Tukwila. It was 1 mile away from where we built DOS, right? Mm-hmm. That experience of just hearing the frogs croaking and hearing the sandpipers and all that stuff, that was an exciting moment in my life and very impressionable upon me. And then 1 mile from there, we're building DOS. If you will, it's the logos of Tim Patterson, his ideas, his mind is in this operating system. One's digital, the other one is analog. And so what I do is, I have a ranch here, and I surround myself with 12 different species, bison and yak and horses and donkeys and sheep and goats, pigs, birds, fish, bees. I like to surround myself because each of these species has something to offer, obviously, the world. I mean, we can't live without them, and they all sort of depend on each other.
Mm-hmm.
You look at things like the bees that I have. I got a beekeeper who comes to keep them alive. Bees are difficult to keep alive because they have a mite problem and diseases.
Yep.
But these bees, if you think about it, they're all these autonomous actors, if you will, that collaborate with each other. They actually use protocols, but we don't call them that in biology. We call them pheromones, right? And so like the queen bee, she's making sure that they keep the hive at a certain, like 95 degrees and a certain humidity all the time. If you see a swarm somewhere, she's in the middle there, and they're keeping that at 95 degrees at a certain humidity. But what she does is she puts out a protocol, saying we need to do this, we need to do that. The bees respond to that. They go out and collect, food from plants. And when they interact with a plant, they also have sort of a protocol where they hum around the flower, and the flower opens at a certain frequency, middle C. And so you see this dynamic between this one organism, a bee, and a flower, and they have this interdependency because the bee needs to pollinate the flowers give protein to the bees take it back to the hive. They all interoperate through an idea called stigmergy, where they just sort of work together, just kind of bumping at each other, say, I'll do this, you do that. That type of collaborative, autonomous operation is how the world works, right? The way bison collaborate with each other, the way yaks work as a herd, the way sheep operate is different. I have my own breed of sheep. I crossed two different breeds to create my own so I could run with them. So I have my own running sheep. So I do some experiments like that. But you get to know this analog world really, really well when you're immersed in it. So when you come to work in something that's fake, like what we're doing right now, just a bunch of transistors changing state, trillions of them at once, right now when we're talking, it's not really real. But you want to take an analog of the analog world to the digital world and say, well, here's how things should operate. Like bees have security mechanisms, right? Certain bees will sense something to go out and attack to keep a predator away, right? That's the kind of security protocol you need, on your paranet, if you will. You need these observers that are watching what's going on to make sure nothing comes into the hive and destroys it. And so I take just things from nature that I observe, because I'm around them every day, and I like to apply those principles to how we develop software, systems, networks, protocols, languages, and so forth.
I love it, Jim. It is really fascinating what you're doing, and I'm super keen at some point to do this in person at your ranch. At least have an opportunity to walk through your ranch and get to understand more how you're thinking about this, how nature and biology and the world that we live in, obviously the as you said, that it's not real, but the digital world that everyone's building. It's truly fascinating. Jim, it's been a pleasure having you on the show. I want to wrap up with one final question. We always wrap every single episode with a recommendation from the guest, a book recommendation from the guest. So we'd love to have one from you. What would be a book that you'd recommend for our audience?
Well, the book that most epitomizes what I've been talking about in terms of your inflection points was the book called The Dream Machine by Mitchell Waltrip. And The Dream Machine is, back in the early days of MIT, when, pre-ARPANET and then ARPANET and pre-internet, the vision of all these computers connecting together is a fascinating story. It's a must-read. Probably the best book I've ever read on the history of computing. If you don't read the history, you don't really understand that you're on this huge trend and why you're on this trend.
Sure.
The trends make more sense when you've read the history behind them.
Yeah, I always say to understand where you're going, you need to know where you came from. So definitely agree with you on that one. Yep. Jim, it's been a pleasure. Thank you so much for making the time to be with us on Inside Silicon Mind, and really excited to do this again at some point in the future.
Right. Really enjoyed it. Thanks.
Thanks, Jim. Thanks for tuning in to another episode of Inside the Silicon Mind. This podcast is powered by Harrison Clark. For more episodes, don't forget to subscribe and hit that notification bell. As always, stay curious, stay consistent, and stay inside the Silicon Mind.